Okay. So Ki, as discussed with you over the LinkedIn also, you talked about the 100x sensitivity improvement in the TMR sensors. So my first question is related to that only. So what are the key breakthroughs that enable this 1000x sensitivity improvement in the TMR sensors?
Yeah, sure. So we are looking at the TMR sensing not just as a sensor, but as a solution, as an end-to-end solution. And that 1000x gain will be achieved by having better TMR stacks and that are integrated to ASIC as well. And then they are in the pipeline of data processing. So we would be achieved about 1000 times gain by concatenating these three components. One is the sensor itself, the TMR sensor itself, having improved stacks. The second one is ASIC adjustment to that. And the third one being the use of artificial intelligence to enable the reduction of noise in a measurement.
Okay. So the AI is basically helping to reduce the noise. Okay.
Absolutely.
So what design considerations are critical when targeting 1000x increased sensitivity?
Yeah, so I think there are two key design considerations. So in achieving this level of performance, we have to ensure that the sensors remain small, such that they would be, it is possible and conceivable to integrate them into diverse applications, from consumer electronics to health and other applications. So the size of the sensor remains a critical factor. And the second critical factor is the power consumption. These new sensors and this next generation of TMR sensors are designed for applications in which power consumption has to be limited, because these are wearable and portable applications rather than application in the automotive industry, where access to electricity and power is abundant.
Okay, so what is the role of ASIC in this?
So the role of ASIC is that, the TMR sensors act as simple resistors. And these resistors can be used on their own, or they can be used as part of a pipeline of data. So in many applications, when the sensitivity or the noise performance of about 1 picotesla is required, additional gain can be achieved by having the ASIC very close to the TMR stack. And that way we would be able to measure the signal, filter the signal at source, amplifies it, digitize it, and then put it on the data pipeline.
So how would you how to design a test setup to verify the claimed sensitivity improvement? How do you test it?
Right. So we have in-house a significant array of test equipment, including a magnetic chamber, as well as a magnetic room, where we can create a known magnetic field and put the sensor inside the chamber and measure the known magnetic field. That way, we would be able to verify the effectiveness of the sensor itself. In addition to that, we have a large number of applications. For instance, putting the sensors on the wrists, such that we would be able to measure the magnetic field from the muscles in the forearm. And we know these magnetic fields from the forearm have very clear kind of signatures in the magnetic domain. And once our sensors be able to measure them, therefore we would be able to verify the fidelity of these sensors.
Okay, so how would the sensor packaging and shielding requirement change when there is an increase in sensitivity?
Correct, and that's yet another reason why we need the ASIC to be very close to the sensor. So we deal with the noise and the environment noise in three different ways. One is by having kind of static shields inside the noise inside the sensor. than having the ASIC being very close to the sensor itself, and therefore we would be able to cancel out interference that are coming from other sources, excluding the source of interest. And then down the pipeline, we have a machine learning, which would be able to kind of detect the signatures of the signal of interest versus the signals that are coming from sources that are not our signals. So it's an integrated approach, a pipeline approach, rather than a single sensor approach.
Okay. Okay. So, as you said that AI is being used for, reduction of noise. So, how AI is helping in doing that?
Yeah. So in our particular application that we are looking at gesture recognition, for instance, we want to put the sensors on the surface of the skin, and then when a person makes a gesture, then we would be able to detect this. So the AI is used, or machine learning is used to map the recording signals onto the gestures of interest. And any signals that do not fit into that statistical description of the signal of interest is considered noise. And that's how we use machine learning to address the noise. So in any application, you have a signal of interest that has a very clear characteristics, and you have signals that are not in your interest. And therefore, the machine would be able to dissociate and distinguish whether the signal is in your interest or it is not in your interest.
Okay. So, how this new generation of TMR sensors are different in structure, or are there new materials that are being used which were not used previously?
So there are if you look at the literature, there are all sorts of exotic materials that are out there to be able to increase the sensitivity of these sensors and improve the noise performance. And you can have TMR ratios up to about 600%. But many of these sensors, many of these laboratory and academic experiences do not map directly onto the reality of the semiconductor industry, where the targets are very limited, and the danger of contamination, basically material contamination in the semiconductor facilities are huge. So what we are trying to achieve in our fabrication process is to stay as much as possible true to the existing target, to the existing material, and be able to adjust the parameters of the existing material to be able to achieve that 1000x gain. So it is doable, it is possible, but then the approach is the combination of basically looking at low TRL science and physics of TMR sensing, as well as what is achievable at a standard semiconductor facility.
Okay, so are these sensitivity changes are because of material, or because of design, or because of fabrication? What is the, most attributable thing in these improvements?
Yeah, so it's the most attributable part is that the combination between the material change, number of layers, the thickness of layers, that kind of a change, as well as the transducer design. So the interaction, the interplay between the transducer design as well as the material change it has been able to bring us this success.
Okay, so how scalable is the improved TMR technology for, very high volume manufacturing?
With the design, if you remember, I said that earlier, we started kind of to stick to the existing material and non-exotic material that are out there to the extent possible, and therefore it is perfectly conceivable that you would be able to have hundreds of millions of chips, TMR chips per year, with this new design. So it is perfectly. We from very early stage, we were in discussions with semiconductor facilities and nanofabrication facilities to ensure that we can create hundreds of millions of chips per year. So it is perfectly scalable.
Okay, great. So, how do these sensors behave under real world interference conditions like EMI, temperature swings, or vibrations?
Yeah, sure. So we've been publishing a lot of the kind of performance of these sensors. For instance, in terms of the perturbation and vibration, we have published that result. It's open access available. So with the standard kind of methods for vibration removal, these sensors work perfectly well as well. In terms of the kind of gesture recognition, in every trade show that we attend, we provide kind of real life demos, so people can put these sensors on their own arms and be able to gesture recognition. Only a few weeks ago, when I was at and the team were at Sensors Converge conference, we had a gesture recognition demo with the TMR sensors, and it went really well. And I'm pleased to say that we received one of the best sensors of the year award in the category of wearable technologies and health.
Okay, so what is the minimum detectable magnetic field level now, and what does that enable?
Yeah. So we are, when we started kind of looking at the market and the literature, we realized that there are so many different sensors out there by so many different suppliers, covering the range of 1 nanometer up to essentially 1 nano Tesla to 1 millitesla. But what we didn't see anything was below 1 nanotesla to about 1 picotesla. So we aimed for 1 picotesla applications, kind of development of sensor with a detectivity of about 1 picotesla per square root of hertz at 1 hertz, which opens up so many new applications in health, measurement of the cardiac signals we can achieve. We have applications in quantum computing, we have applications in agriculture, we have applications in robotics. So there are so many different applications that have opened up by pushing the boundaries into essentially achieving a 1 picotesla at 1 hertz noise performance.
Okay. Okay, so so you have given me a lot of applications. So, but how it is particularly helping in quantum computing?
So wherever you are measuring currents in a quantum scale, in a very cold quantum scale, and you would require a sensor that is semiconductor friendly, you would be able to use TMR sensors as well.
Okay, so are there any trade-offs also between the sensitivity and power consumption and speed?
Yes, so there's an interplay of sensitivity, noise performance, and power consumption. These TMR sensors are not are single MTJ stack. Usually there are kind of a series and parallel combination of TMR stacks, and it is conceivable the more resistors that you have, then you perhaps increase your detectivity, but then your resistance increases as well. So these are combination of different factors. And in fact, what we have been able to develop is a whole simulation kind of a platform such that we would be able to simulate all eventualities before fabrication. And that's one of the reasons that we've been accelerating the design of this next generation TMR sensors, because we have the whole capability of simulating performance, then building it, then measuring it, and using the measurement to enhance our simulation capability. So it's a co-design of software and hardware at Neuranics.
Okay, so what are the main challenges when integrating these sensors into, into the devices?
So the main challenges, as I mentioned earlier, are the size of these sensors in terms of the physical dimensions, as well as the power consumption of these sensors. Assuming that the performance in terms of a noise level is achieved, then two other factors are the size and power consumption. And importantly, different applications, they have different size and power consumption requirements. What we have so far been able to kind of develop is that core development of the MTJ stacks and the TMR sensors. And then we worked collaboratively with our clients and customers to be able to adapt our sensors to their requirements. For instance, we work with tier 1 and OEMs in terms of proof of concept projects, and demonstrate them that the TMR technology is a conceivable approach to meeting their requirements, and then work with them to scale up the operation from a few samples to perhaps hundreds of thousands of samples within a short scale of time.
Okay. Okay. So you also told that there are, various applications in which this is very much applicable. But like you talk about the healthcare or whatever application. So TMR sensors that were before, not that high sensitivity, but they were also applicable in those, applications. So how it is making a difference?
Yeah. So the TMR sensors that have been used in medical applications, they have only been used as a switch. So an on and off switch, for instance, for the kind of continuous glucose monitoring systems or other applications. Mainly they have been used as a switch and essentially replacing whole sensors. The way that we are using them is in terms of a sensor. An analog sensor would be able to measure on a kind of a linear way the amount of magnetic fields. And by doing that, you open up totally different ways of looking at the biomedical or biomagnetic signals, magnetic signals from the body, as well as the magnetic signals that are coming from the, in other kind of current applications. But specifically for the medical application, to the extent of our knowledge, most of the TMR sensors have been used only as switches. Although I have to say there are proof of concept demonstration that TMR sensors can be used for the measurement of cardiac signals, heart signals.
So how accurate they are in measuring the cardiac signals?
As a proof of principle, they have been successful. However, most of the sensors that these testing have been done, they have been done inside the magnetic chamber, as well as the sensor sizes are fairly large. You're thinking about several centimeters even at some points. So as a proof of principle, they have been demonstrated successfully, yet it is inconceivable to have these sensors on a larger scale manufactured and millions of people wearing it and going about their lives. So we are at that transition of making these kind of laboratory demonstration to successful kind of digital health type products or gesture recognition type products.
Okay. Okay. So are there also some industry standard benchmark?
There are some TMR industry standard benchmark for in the automotive sector. However, when it comes to kind of wearables and XR type interfaces that we are working on, we are the frontier. We are at the frontiers of this development, and we would be very happy to work with other players in the market to create these standards.
Okay, so are there some emerging materials or structures that could push the TMR performance further?
Yes, research at the academia is right at that cusp of coming up with new materials to push the performance even further. And research is ongoing. Papers are published on it on daily basis about different materials. Like I said, TMR ratio is about 600%. Is achievable in laboratory settings at the moment. What is not clear yet is the areas of where these sensors could be used currently, because we are at the stage of a picoTesla kind of defining new markets for picoTesla sensitivity. And when it comes to femtotesla sensitivity, I think the critical thing is that we defined what markets could benefit from that level of sensitivity. And secondly, there are technologies in the femtotesla range. There's the classic squid technology or other technologies that kind of are designed for the femtotesla range of sensitivity. So I think and obviously the optically pumped magnetometers. The key question is that even though it might be conceivable to have TMR at the kind of femtotesla level performance, then what are the kind of these defining applications such that justifies major investment for scaling it up, the TMR technology? At the stage that we think that the picotesla range from 1 picotesla to 999 picotesla, it's an area that has been underutilized and under commercialized. And once we get the level of maturity in the picotesla sensitivity, then it, of course, as the femtotesla sensitivity comes after it.
Okay, so you talked about the wearables, that it can be used in wearables, like you talked that it can be put on the wrist. So can these sensors be also used in flexible or fabric-based wearables?
Yeah, it could be. They could be used in flexible or fabric-based wearables, because if you kind of consider these sensor dimensions are, about hundreds of microns, and including the ASIC chip and wireless transmission and all of that, you're talking about a few millimeters by few millimeters. So it is easily conceivable that these are on flexible platforms, including fabrics. They would be integrated. So I can easily foresee a future where we have these sensors kind of integrated into the fabric of the clothing that we have, and clearly, because they are non-contact, because they are magnetic, they would be able to measure magnetic field from the muscles, or a magnetic field from the heart in a medical applications. We are kind of very much a technology company, so we are pushing for the kind of next generation of technology, and we are willing to work with many clients to be able to design bespoke sensors for their applications.
Okay, so do you also think that in coming future, this TMR sensors can replace the other type of sensors in wearables?
So interestingly, these the TMR sensors are kind of appropriate for many measurements, but this notion of kind of replacing all of the existing kind of sensors in wearables uh, is probably not going to be a realistic target. But though it is realistic, is that in many applications you can remove or replace some of the existing sensors in the wearables and replacing that with TMR. For instance, if you're looking at the kind of PPG sensor in wearables, the one that kind of measures the oxygenations of the blood, the so-called, it estimates the oxygenation of the blood. So if the heart rate is a measure of measure of interest, then TMR sensors could easily be used to approximate heart rate. If, for instance, the blood pressure is of interest, then TMR sensors would be able to use. But perhaps they are not really good in estimating the body temperature that comes from the PPG sensors as a byproduct of PPG sensors. So these are different applications, and therefore clear thinking and planning is required to achieve them. But I'm sure as we progress and we work with wearable manufacturers, there are many applications that they come about because of this generation of sensors. We are supplying customers with applications that only 18 months ago it was unimaginable even for us.
Okay, so you also talked that can be used in quantum computing. So are these TMR sensors sensitive enough to measure the very small magnetic changes in quantum system?
That remains to be seen. In theory, it is consumable. In application, we need to see we need to interact with the quantum computing manufacturers or designers to be able to integrate these sensors into quantum computing.
Okay. Okay, so what kind of sensor fusion approaches you are exploring? Gesture recognition, or also in wearables you were talking about?
So at the moment, we are not considering any kind of sensor fusion methodologies. These methodologies are available in the literature from the 70s. So we are currently working kind of single modality TMR sensing, single modality in terms of for our application. Obviously, you can consider addition of other modalities, for instance, optical sensors, for instance, the standard MEMS magnetometers, to achieve to give you multimodality, and therefore you would be able to use sensor fusion. But at the moment, we are single
Mhm.
modality TMR sensor solution company.
Okay. Okay, so are there also any specific type of magnetic signals in the body that TMR sensors are uniquely suited to measure?
That is right, yes. So, for instance, the electrical activity of the muscles, when you want to move your hand, your brain sends a pulse to your muscles, and then those muscles move your fingers, right? So those electrical impulses, they create local magnetic field in the range of low picotesla, sub 10 picotesla sensors, and they are essentially it is not feasible to measure them with electrical sensors because they are magnetic signals. And many other magnetic sensors that are out there are too bulky, like a squid, to be able to be made a wearable, or like the existing TMR sensors, 1 nanotesla TMR sensor or Hall sensors, they don't have that level of sensitivity to this level. So therefore, low picotesla or sub 10 picotesla TMR sensors are best and also uniquely suited for this particular applications.
Okay, and also what design challenges do you face in designing high sensitivity TMR sensors?
So I'm going to refer back to kind of the earlier comment that I made. Making TMR sensors at 1 picotesla sensitivity or slightly even lower is a addressed challenge for us. Well, it was a challenge for us. It's now been addressed. Making these sensors in small size with lower power consumption, with large dynamic range, all of these other factors that are interplay, these are key design challenges. Making these
Mhm.
sensors small so that the whole chip with all packaging, you're talking about a millimeter squared, or the power consumption to be kind of very limited, because many of the gesture recognition algorithm, many of the gesture recognition kind of systems, they use more than one sensor. So you're looking at like 8, 10, or 15, 16 sensors. And so individually, they need to be very, very low power, such that the overall profile for 16 sensors are kind of within an acceptable range.
Okay, so what is your next research or development milestone will be? Are you working towards decreasing the size of the sensor or increasing the sensitivity? What is the main goal?
So we have this multi-pronged approach. The kind of key design factors are sensitivity, stability in terms of sensitivity, lower, smaller dimension, and lower power consumption. And our kind of key target is to demonstrate our gesture recognition system at CES 2026.
Okay, great. So,
So we
uh,
demonstrated the
mhm,
four-channel system at Sensor Converge 2 weeks ago, 3 weeks
mhm.
ago. So we are now scaling it up to a much more sensitive platform that works in a very magnetically very noisy environment of CES in January 2026.
Okay. Okay, so you also talked about the simulation and software. So, is that also helping in enhancing the output?
Absolutely. We minimize the number of times we could make errors in fabrication by doing a simulation. So we look at all different eventualities in terms of sensor design, in terms of stability of the sensor, dynamic range, power consumption, all of in our models, and we select a few that we think that they have highest likelihood of success, and then manufacture those. Once we have manufacturing, we bring them back to the laboratory, do our measurements, refine our models, and we go for the next round of manufacturing. And that's where we can accelerate our kind of a lab to manufacturing and back to the lab cycle. And we would be able to kind of essentially minimize the number of incorrect design decisions.
Okay. So the software you're using for simulation is like the open source or is your proprietary tool? What you're using?
It is Neuranics software. It's not a commonly available
Mm-hmm.
tool. It is a Neuranics piece of software that sits on about 50 years of the kind of collective person years of development of TMR sensors in Neuranics. Neuranics is a deep tech company spun out from the universities of Glasgow and Edinburgh, and many of our R&D team are PhD graduates with several years of experience working in our laboratories at the university sector and as well as in the industry, joining Neuranics. So we are on the search for the brightest and the best minds on the planet on the TMR sensing, and we have several positions open if people are interested in joining us.
Okay, so I think this will be my last question. So as you talked about AI is helping in the reduction of noise. So in future, what other things the AI will be able to do with to improve the sensitivity of the TMR sensors?
So I'm going to go back, give you, for instance, an example. Once we have this sensors, once the integration between AI and the sensor and the ASIC, this pipeline is complete, then AI would be, and it's, for instance, imagine that you put these sensors on your chest. The AI would be able to detect between arrhythmias in the kind of the so-called magnetocardiograph signals, but not in the hospital environment, but in people's home environment. The AI would be able to predict the likelihood of a kind of a stroke or ischemic heart condition before it happens. So you can kind of bring back people who are at the risk and they've received this monitoring device, bring them back to the lab, to the hospital environment and provide care to these people. So AI, the key element is that we use the AI for essentially noise reduction, removing the signals that are not in our interest from the signal that are in our core interest, the so-called the magnetic signals. And based on that, you can have other kind of blocks of AI doing various different applications, from gesture recognition, from heart and cardiac monitoring condition, from predicting falls in people, old people with older age, from the development, from the kind of progress of a cancer in a person with different conditions. You can have all different applications envisaged at the pace that AI is developing as well.
Okay. Okay. So is there any new product launch recently in this TMR sensor field by your company?
There are many companies active in this field,
Mm-hmm.
and there has been kind of a few larger scale mergers and acquisitions recently. Most of the sensors that are out there, if not all, are in the nanotesla kind of range. We are not aware of any product release in the
Mm-hmm.
picoTesla, although there are examples of picoTesla sensitivities out there. However, they have been online and public material for a long time.
Okay. Okay, Kia, I think I'm done with all my questions. Okay, thank you. Thank you so much for your time.
Wonderful. Thank you.
Thank you.